We are going to discuss this chapter on practical circuits, which is chapter 12. And after completing this chapter, you should be able to explain the effects of internal resistance on terminal potential difference and power output of a source of EMF. We will learn what internal resistance is. We will see what terminal potential difference is. There is an equation which has these quantities and the power output of a source of EMF. So source of EMF is a power supply. We use the word EMF only for power supplies. For example, batteries, cells, dynamos, generators. Solve problems involving the potentiometer as a means of comparing voltages. So here is another topic, potentiometers. We will see the details. And also we have potential divider. Now there will be a similarity between some of these topics. We will see them when we discuss this lesson. Okay, so the first thing is internal resistance, and whatever is in green bold letters or whatever is highlighted in green in this textbook is very important. Let me just show you. For example, you can see some important definitions or meanings of certain words highlighted in green. Now in this chapter I don't think it's there, but in other chapters it is there, where important definitions or meanings of important words are highlighted in green. So let me just quickly show you. For example, if we go to the previous chapter, you can see Ohm's law is highlighted in green. Whatever is highlighted in green is very important. You have to memorize it with understanding, because in the exam they can ask you to write this definition. So make sure you write it with the keywords. If you try to write it in your own words, you might miss certain keywords. That's why I ask you all to memorize these definitions with understanding. Let's go to the next one, practical circuits. You should be able to, so this is what we will see now. First thing is internal resistance. What is internal resistance? For every power supply there can be a resistance inside itself. This is what we call internal resistance. For example, for a power supply this may be due to the wires and components inside, whereas for a cell or battery the internal resistance is due to the chemicals within it. Experiments show that the voltage across the terminals of the power supply depend on the circuit of which it is part. So what is important here, now you can see this diagram. Figure 12.2 shows a circuit you can use to investigate this effect, and a sketch graph showing how the voltage across the terminals of a power supply might decrease as the supplied current increases. By moving this, this is a variable resistor. I have a video explaining how to use the variable resistor. You can watch that. Now what happens is, when you move this sliding contact, this arrow represents the sliding contact in the variable resistor. If you move it more to this side, to the left, then the length of resistance wire that the current passes through is less. You have learned the equation R equals rho L over A in the previous chapter, chapter 11. You learned about resistivity, and in that you had the equation R equals rho L over A. That means when the length of resistance wire decreases, the resistance decreases. So what happens is, when you move this sliding contact or arrow to the left, the length of resistance wire that the current passes through decreases, which decreases the resistance in the circuit. So you can see then what happens to the current. V equals IR. So the R decreases means the current increases. Now we will see the details about this. A circuit for determining the EMF and internal resistance of a supply. Diagram A, typical form of results. We will see how to draw this graph, and that is very important, where you can use it to find the internal resistance and so on. Okay, and when you learned about potential difference, EMF, voltage, you learned that the power supplies or batteries supply energy to the chargers to push them around the circuit, whereas at other components like resistors, lamps, where the electrical energy is converted to other forms, this energy is used up. The charges moving around a circuit have to pass through the external components and through the internal resistance of the power supply. These charges gain electrical energy from the power supply. This energy is lost as heat as the charge passes through the external components and through the internal resistance of the power supply. So some of that energy is lost inside the power supply itself due to the internal resistance of that power supply. Power supplies and batteries get warm when they are being used. Try using a cell to light a small torch bulb. Feel the cell before connecting to the bulb and then feel it again after the bulb has been lit for about 15 seconds. So inside the power supply or inside the battery itself, there is heat produced due to the resistance. So when the charges pass through this, because they have resistance, it produces heat and energy is converted to other forms. This is what we are talking about over here. In addition to the chargers losing energy outside the power supply or outside the battery, there is some energy lost or converted to other forms, for example heat, inside the power supply itself due to its internal resistance. And you can observe it like what they have mentioned here. The reason for this heating effect is that some of the electrical potential energy of the chargers is transformed to internal energy. Internal energy also we can say is heat. Now there is a difference between thermal energy, internal energy and heat. So you have learned that, I think even in the O-level class. I have uploaded a video explaining all this. You can watch that video for more details. Okay, as they do work against the internal resistance of the cell. Okay, and by the way, the EMF is not equal to the potential difference across the cell or power supply if it has an internal resistance. If it doesn't have internal resistance, which is what you would have seen so far, the EMF is equal to the potential difference or voltage across the power supply or battery. But when there is internal resistance, the EMF is greater than the potential difference across the power supply, which we call the terminal potential difference. You will be familiar with the idea that when you use a power supply or source of EMF, you cannot assume that it is providing you with the exact voltage across its terminals as suggested by the value of its EMF. There are several reasons for this. For example, the supply may not be made to a high degree of precision. Now that can be another reason, and we will see how we can get it equal to the EMF. So if you connect a voltmeter directly across the terminals of a power supply, then since that voltmeter has a very high resistance, the reading it will give in that case will be equal to the EMF of the cell. So this is how we determine the EMF. But if you connect the cell to some other component and then connect the voltmeter across it to find the potential difference across the power supply, it will be a lesser value than the EMF. So later on we will see that in this chapter. So to a high degree of precision, batteries become flat, that means they die, and so on. And also what happens is, with time, when the battery is getting used up, its potential difference value decreases, its EMF value decreases. In the beginning, let's say you have a cell which is 1.5 volts, but later on it will decrease to maybe 1.0, 0.5. You can observe that if you connect a multimeter where the settings are in the voltmeter settings across a new cell that you just got, it will read maybe 1.5 or 1.6. So after using it for a certain time, now you may be using these small batteries in clocks and other electronic devices. You can take one out when it has died and then check the potential difference across it. You will see that it will give a smaller reading. Okay, then one of the more important factors, which is that all sources of EMF have, that is internal resistance, which shows that smaller value for the potential difference across the power supply compared to its EMF. And here you know the reasons for the internal resistance. That internal resistance causes the potential difference to be less than the EMF. Okay, so this page is explained. Now we will look at the next page. Now this is where you have the diagrams and the equations. This is very important. If in the exam purpose also, if a cell or battery has an internal resistance, then a dashed rectangle is drawn like this, and that internal resistance is represented by a resistor symbol like this. We use simple R to represent the internal symbol for the internal resistance. So this is the dashed rectangle, and whatever is drawn inside that is used to represent what is inside that cell or power supply or battery. Then this is used to indicate, we write the letter E on top of this or the bottom, and this is the internal resistance. We use the symbol simple R. For the resistor which is outside the power supply, outside the battery, a capital R is used. So remember, this symbol simple R is only used for internal resistance. Now if you look at this circuit, we can write an equation for this. Having all this, previously you learned the Kirchhoff's laws or Kirchhoff's laws, first law and second law. In the Kirchhoff's second law, it was stated that the sum of EMFs around a loop is equal to the sum of potential differences around that same loop. And you have learned the Ohm's law equation, V equals IR. V equals IR. So the potential difference across this resistor, for example, is I times R. I times capital R. Across this will be I times simple R. So that means the EMF, according to the Kirchhoff's second law, the EMF is equal to I times R plus I times simple R. So this is what we get. Now I is common, we can factor it out because it's the same current passing through each of them. You can see all of them are connected in series. Then this V times this R is the same as the potential difference across the terminals of the power supply or cell. It is the same as the potential difference across this resistor capital R. So what is that? V equals IR, and we call this the terminal potential difference. Terminal potential difference. So we have this equation. We can replace the I times capital R with capital V. Okay, so we have that, and we can write the V there, rearrange the equation, then you will get this. So E equals V plus IR, move the IR to this side, then you get E minus IR equals capital V. That is what we have here. E minus IR equals capital V. Now V is the terminal potential difference, E is the EMF, and I times R. Now again you can see V equals IR you have learned. So here also this is a voltage, but that voltage is due to the resistance inside the power supply or battery. That's why we call it lost volts, because you can't really see it since it's inside the cell itself. Okay, that is why it's called lost volt. Now this we can see, we can connect a voltmeter across this, and we can read the meter and see what the value is. But here inside this we can't see it using a voltmeter. That's why it's happening inside the cell, so we call it lost volts. You can remember it that way. Now this is the equation. Now you know how to derive it. We use the Kirchhoff's second law. We got this and then rearranged it. Remember, I times R is capital V, and then we get this equation is important. Now, if you are not able to remember this equation, you can remember this. You know how to get this from this diagram using the Kirchhoff's second law. That can be rearranged to get this. Remember, I times capital R is capital V. Replace that and you finally get this equation. So The lost volts indicate the energy transferred to the internal resistance of the supply. If you short circuit a battery with a piece of wire, a large current will flow. Now what happens is, if you short circuit, then there will be no R, capital R. So that will be 0. If you use a wire has a negligible resistance, so we can say R is 0 then. Okay, so that's what we have here. The lost volts indicate the energy transfer to the internal resistance of a power supply. If you short circuit a battery with a piece of wire, since that resistance is 0 then outside, the lesser the resistance, the larger will be the current. A large current will therefore be drawn from the battery. A large current will flow and the battery will get warm as energy is transferred within it. This is also why you may damage a power supply by trying to make it supply a larger current than it is designed to give. So that can damage the power supply or battery. Okay, so make sure you answer these questions. These questions are related to what you are learning here. To help you all understand this better, let's go through another example, worked example. There is a current of 0.40 amperes when a battery of EMF 6.0 volts is connected to a resistor of 13.5 ohms. Calculate the internal resistance of the cell. So very easy, we can use this equation. Remember, simple R is the internal resistance. Simple R times I will give you the lost volts. If you want, you can write down the quantities that are given in the question like this, and then also write the equation that you are supposed to use. You can figure out the equation that you are supposed to use by first writing down the data that is given here and finding which equation has all these quantities E, I and R, and that is also, you can write simple R here with a question mark because you're supposed to find simple R. Okay, so then that equation is this one. See here, same thing. We use this because if we use this, we don't know V yet, then that means we will have to find V using this and then substitute it here, but it's easier to directly use this or this. So let's do that right now. First we can write down the quantities. The EMF of the cell is 6.0 volts. The current is 0.40 amperes. R, the resistance of the external resistor, that is the resistor outside the battery, which is connected to the battery, that has a value 13.5. Now simple, you can use this equation and find simple R. You will get 1.5 ohms. You can try this question by yourself. That means the internal resistance is 1.5 ohms. So make sure you answer all these questions here. Then another important thing you have to do is the graph. Now remember, if you go back to what we saw it here. So we will see how we can draw this graph. It's very simple. Okay, so what we will do is use this equation, rearrange it, put it in the form y equals mx plus c, and then you will see that which is the gradient, which is the y-intercept, and you will see that it is this. So for example, we can even write it down. Okay, so we'll write it down and do it because that will make it easy for you to understand. Okay, before we do that, let's quickly go through this. You can get a good idea of the EMF of an isolated power supply or a battery by connecting a digital voltmeter across it. So what you can do is EMF, like I said, it's actually explained here. Okay, the effect of internal resistance and all that. So what happens is, when you connect a voltmeter directly without any other component directly across the battery or cell or power supply, there is no external resistance, and the voltmeter has a very high resistance, so a very small current passes through the voltmeter, which effectively makes this term 0. If you understand, because the current is very small when you connect a voltmeter. Maybe I can draw it and show you. So let's say you have a cell, and across this cell only a voltmeter is connected. So here is the symbol for voltmeter. The voltmeter has a very high resistance. You can say R is very high. Oh, I should have drawn the internal resistance. Let's do that. So this cell has an internal resistance. Just erase this part and I will draw it now. Okay. So remember, when we do this, we draw all these two inside a dashed rectangle, which indicates that it is the internal resistance of the cell. If you have several of these, that means it's a battery. So you know the difference between a battery and a cell. A number of cells form a battery. Okay, the symbol we use for this is simple R. Here we use epsilon or capital E. Now this is all we have, and remember the equation we had. If you remember, it's V equals E minus IR. Okay, how we got this? You can see what we learned earlier. So I directly use this, and let me just show it to you. Okay, so this is what we have, and I showed you how to get it. V equals E minus IR. We have this. Now what happens here is, because the resistance of the voltmeter is very high, the current is approximately 0. So here we can say this is approximately 0, almost 0. So if that I is 0, what happens? This I is equal to 0. That means this whole term is equal to 0. So which makes, okay, so we can say since I is 0, so let's write that down. Okay, so here you can say since, okay, pause it and write it. Okay, so now it's very clear. So what happens is, you can see the current will be very small. When this resistance is very high, the current will be very small. It's approximately equal to 0, which means that I have written it here, which means this term, this whole term becomes 0. I times R becomes 0. I times R is the lost volts, so that becomes 0. Therefore V, which is the reading on the voltmeter, V then will be equal to E. So what happens is, the voltmeter measures the EMF of the cell, and this is how we measure the EMF of a cell. To measure the EMF of a cell, we connect the voltmeter only across the cell. So it's only the voltmeter and the cell. When we connect it like this, the reading on the voltmeter is the EMF of the cell. So here we can also say R is very high because the voltmeter has a very high resistance. Okay, so here we can write because voltmeter very high resistance. Voltmeter has a very high resistance. Ammeter has a negligible resistance. So you should know this. You should have already learned that in the O-level class also. Okay, R is very high. Alright, so I have written it like this. Now see, R is the resistance of the voltmeter. You can compare this diagram with what you have here. So what we have here is the voltmeter, and the voltmeter has a resistance R, and it is very high. That's why the current in the circuit is almost 0. Now the lesser the resistance here, now instead of voltmeter, if we directly connect with the wire, then the capital R will be very small. So it will, therefore it will draw a very high current. Okay, so we got this equation from V equals I'll write that also here. V equals IR minus I simple R. Okay, sorry, not this one. Yeah, this is what we have. So V IR equals E. Remember, this is I times capital R minus IR. Okay, so now I think everything is very clear from here. Okay, let's go back to the lesson now. Okay, so anyway, this is the lesson, so you will understand all this. Okay, we were discussing this. You can get a good idea of the EMF of an isolated power supply or a battery by connecting a digital voltmeter across it. Isolated means it's only the power supply and the voltmeter. That's why we say isolated. A digital voltmeter has a very high resistance. See, it's about 10 to the power 7 ohms. So only a tiny current will pass through it. So there's a small current. Even when you connect the voltmeters, like for example across some external resistor, there is a small current flowing through the voltmeter to power it. Otherwise you can't. If you just have the terminals outside, it won't give a reading. Terminals of the voltmeter. If you want to determine the internal resistance, current will pass through it. The lost volts will then only be a tiny fraction of the EMF. That's why I could approximate it to 0. If you want to determine the internal resistance R as well as the EMF E, you need to use a circuit like that shown in figure 12.2. When the variable resistor is altered, the current in the circuit changes, and measurements can be recorded of the circuit current I and the terminal potential difference V. So what is happening here is we have a graph of V versus I. Now how do we get this graph? Actually it is from this equation. So let me write it and show you now. Alright, so here is the working now. So I have shown the diagram here, and you know how to get this using the Kirchhoff's laws, KVL, Kirchhoff's voltage law. You can get this. Then okay, so here I have written using Kirchhoff's second law, we get this, and which states that the sum of EMFs around a circuit is equal to the sum of potential differences around around a loop is equal to the sum of potential differences around the same loop. So here we have the EMF when you go across this and across this. When the current goes, you get the potential difference across this, potential difference across this. The potential difference across this is called the lost volts. R is the internal resistance, V is the terminal potential difference, and this is the EMF. Now this V, we can write it as I times R. Okay, I times capital R. You see here, I times capital R. Alright, now to draw this graph, the point of drawing this graph is from the graph we can find E and R. E is the EMF, R is the internal resistance. So you can see I have written this equation again over here and rearranged it. I made E the subject, V the subject of this equation. So I move this term to this side, and then I write minus I times R first, then E second here. You can see, and multiplication is commutative. So I can write it like this over here. So we have Y equals mx plus c. M is the gradient, x is what we have on the x-axis, that is the current. On the y-axis we have V. That's why I put this in this form, Y equals mx plus c, where Y is V, x is I. Then the y-intercept is the EMF, the gradient is minus R. So what you can do is, when you plot this graph, you can find the gradient. The gradient will be minus R. So once you find the gradient will be negative, and because it is equal to minus R, you divide by minus 1 and then you get R. So the gradient is minus R. So R is equal to minus 1 times the gradient. Anyway, the gradient is negative, so minus times minus will give you plus. Then the y-intercept is E, the EMF. Okay, so here you can see I have written it here, and this is how we find the internal resistance and the EMF. You should be able to rearrange equations like this, especially in paper 3 and also later in paper 5. You are given equations like this where you have to rearrange them and put it in this graph form and find the gradient, find the intercept. Especially in paper 3, question 1, the last part is where you have rearranging equations like this to find the constants like gradient, intercept. Now here you can say R is a constant. It's the internal resistance, it doesn't change. EMF is also a constant, it doesn't change. So in paper 3 there is a question like this in one of the past exam papers where you need to find the EMF and the internal resistance. Okay, so now I think this is clear. When the variable resistor is altered, so if you go back to the diagram here, using this you can change the current through the current in the circuit. So as a result, the terminal potential difference also changes. Let me crop this also. Alright, so let's have a look. Now we have this. Yeah, so you can see this is the diagram. So using the variable resistor, by moving the sliding contact, we can change the resistance in the circuit. That will change the current. So if you move this way, the current in the circuit decreases. If you move the current in the circuit increases if you move it this way, because the resistance in the circuit decreases. So if you move this to the right, the resistance increases, so the current decreases. And also the I times R, that value you can see here, the voltmeter measures the potential difference across this variable resistor. Even if you connect it here, it's again like this diagram here. So when you have variable resistor, the terminal potential difference is the same as the potential difference across this variable resistor. So that value changes. So V is that value that changes. So different values of I, you can get the corresponding values of V and plot this graph. That is what is explained here. So this experiment is very important. When the variable resistor is altered, the current in the circuit changes and measurements can be recorded for the current I and the terminal potential difference V. And these terms are very important. Again, terminal potential difference. So if you connect a voltmeter here or here, it will give the same reading for this place and this place, because this is just a wire. Same thing here. If you connect between this point and this point, but remember you can vary the potential difference. So if you connect here, it will give the it will give, I mean you have to connect it like this from here to here. You can't connect it from here to here because the current is not flowing this way. So from here to here, from this wire to here, you can connect the voltmeter, which is the same as connecting it across this. Now even though the ammeter is here, there is no problem because the ammeter has a negligible resistance, so the potential difference across the ammeter is negligible. It's we can take it to be 0. And measurements can be recorded of the circuit current I and the terminal potential difference V. So circuit current I and terminal potential difference V, X and Y values. The internal resistance can be found from a graph of V against I. So figure 12.5, this is what I explained. Compare the equation, this one. So I showed you all the details here. This is very important. Compare the equation, this one, of a straight line like y equals mx plus c. By plotting v on the y-axis and I on the x-axis, the straight line should result. The intercept on the y-axis is e, and the gradient is minus r. So that is what I have shown here. Okay, then effect of internal resistance. You cannot ignore the effect of internal resistance. Consider a battery of EMF 3.0 volts and of internal resistance 1.0 ohms. The maximum current that can be drawn from this battery is when its terminals are shorted out. So if you directly connect a wire between the two terminals of a battery, then wire has a negligible resistance, so the huge current will flow through it. Yeah, the external resistance R is equal to 0, that is if you connect with a wire. The maximum current is given by this, so we can sketch a diagram for this also. Now or you can even look at the diagram here. Now imagine if we directly connect a wire here, the resistance R will be, capital R will be 0. So then if we use V equals IR for that equation, again, yeah, sorry, we can use this one. Okay, so here what is happening, this term is now 0. Okay, so this term is 0 means E equals I times simple R, which is what you have here. E equals I times simple R. So you get the maximum current. I think you can see it. So when this R, capital R here is 0. That means if you directly connect with the wire, this term is 0. So then E equals I times simple R. So I, which is the maximum current, will be E divided by R, which is what is used here, E divided by simple R. And the EMF is 3. The resistance is the internal resistance, which is 1 ohm, and you get a current of 3.0 amperes, which is the maximum current. The terminal potential difference of the battery depends on the resistance of the external resistor. So you can see the V, this terminal potential difference V, depends on the external resistor, depends on this. It's very clear because it's I times capital R. For an external resistor of resistance 1.0 ohms, the terminal potential difference is 1.5 volts, half of the EMF. Now again, if you can't see it, you can draw a diagram. Again, we'll look at this diagram. So remember, in the example here, EMF is 3, this is 1. So if you connect an external resistor which is also 1 ohms here also 1, here also 1 ohm, then what happens? This EMF is 3 and it divides equally between the two, because if the resistances are equal, the EMF divides equally between them. The voltage across each of them will be the same. So if this is 3 volts, this is 1 ohm, this is 1 ohm, that means across this 1.5, across this also it will be 1.5 volts. That is what is explained here. Half of the EMF. The terminal potential difference approaches the value of the EMF when the external resistance R is very much greater than the internal resistance of the battery. So this is what I explained previously about the voltmeter connected across the terminals of this directly. So if you keep on increasing this, then I had already explained this earlier, when R is capital R is very high, the current here will be almost 0. So then the voltmeter measures the EMF. For example, a resistor of resistance 1000 ohms could connect to the battery, gives a terminal potential difference of 2.997. That means if the resistance here, in the case, so this is 3 volts, this is 1 ohm, and let's say this is having a very high resistance which is about 1000 ohms, then you can find what is the terminal potential difference here. It will be 2.997, which is approximately 3 volts. So this is how we can explain this in that way also. This is almost equal to the EMF of the battery. The more current a battery supplies, the more its terminal potential difference will decrease. Again, if you keep on reducing, if this is very small, it will draw a larger current, because less resistance means the current can flow easily. So a larger current will be drawn. The more current a battery supplies, the more its terminal potential difference will decrease. So you can think of it that way also. An example of this can be seen when a driver tries to start a car with the headlamps on. The starter motor requires a large current from the battery. The battery's terminal potential difference drops and the headlamps dim. So you would have seen this. If you have a car with the lights on, if you start the car, the lights dim. The reason is because the motor requires a large current from the battery that will drop the terminal potential difference across the battery. This requires a large current from the battery, terminal potential difference across the battery drops and the headlamps dim. Okay, so there is a question about it here. You can do these questions, all these questions, because we have covered all the relevant theory so far. Now let's go to the next topic, which is potential dividers. Okay, so from the name itself, I think you can understand what it means. Potential divider. So it divides the potential. For example, like I mentioned before, in the case of the car, Remember, if it is 3 volts and 1 ohm resistor was there here and then another 1 ohm here, then the potential or difference across each of them will be the same. So we will see that again here. So this diagram is there already, so it's much easier to understand. So let's say this battery, now remember you have a number of cells between these two, a number of cells, 2 or more cells form a battery. This is the symbol for one cell, this is symbol for another cell, and this dashed line indicates there are cells in between them. This is a battery. The EMF of that is 6.0 volts. Now here you can see we assume no internal resistance because there is no dashed rectangle and a resistor inside it. So no internal resistance is considered from here onwards because otherwise it will be complicated. How can we get an output of 3 volts from a battery of EMF 6 volts? If the resistance here and the resistance here are the same, and if there are only 2 resistors here in this connection, then the potential divides equally. The potential difference across them will be the same. So it will be 3 volts across this and 3 volts across this because of Kirchhoff's law. The sum of EMFs around a loop should be equal to the sum of potential differences. And also you have learned that the greater the resistance, the greater will be the potential difference across it. Now for example, if this was 400 ohms and if this was 200, then the potential difference across this will be double the potential difference across this. So here it will then be 4 volts, here it will be 2 volts, and the sum 4 plus 2 should be equal to this, which is 6. So if this was 200 and if this was 100 ohms, then across this it will be 4 volts, across this it will be 2 volts. 4 plus 2, 6. How can we get an output of 3 volts from a battery of EMF 6.0 volts? Sometimes we want to use only part of the EMF of a supply. To do this, we use an arrangement of resistors called a potential divider. Now you see this word is in green bold letters, which means it's important. You should know the meaning. If you go to the glossary of the book, the meanings of these types of words are given there. Figure 12.6 shows how 2 potential divider circuits, each connected across a battery. So this is one, this is another one. See, so we can actually use the variable resistor like a potential divider. It has 3 places to connect. One of the wires can be on the sliding contact. Remember over here, this sliding contact. So you have one wire connecting here, another one here, another one here. That way you can use it as a potential divider. Okay, so that is what we have here. See, each connected across a battery of EMF 6.0 volts and of negligible internal resistance. 2 potential divider circuits, this and this. See here, this sliding contact can be moved up and down. So if you move it up, then here the length of resistance wire is less, here the length of resistance wire will be more. But if this was exactly in the middle, then equal lengths of resistance wire on either side of this sliding contact or arrow, which means the resistance R1 and R2 are equal. So then across this the reading will be 3 volts. But if you move this more to this side, the resistance here will increase, R2 will increase. Remember, R equals rho L over A. So when L increases, R increases. When you learned about resistivity, you learn the equation R equals rho L over A. R is the resistance, rho is the resistivity. It's taught in the previous chapter. So if you want more details, go through that, the resistivity topic. Okay. Now what happens here is, if you move this up, here the resistance increases, and remember V equals IR, so the same current is flowing through this. That means when R increases, the potential difference across this will be higher. Here the potential difference will be less because the potential difference across this plus this should be equal to that. Okay. Now if you connect the voltmeter here, it will give the potential difference across R2. Here also is giving across R2. Then 6 minus this value will give you the potential difference across this, which is again equal to 3 volts. 2 potential divider circuits. across the battery EMF 6 volts and of negligible internal resistance. Now how do we know? From the diagram also we can see negligible internal resistance, because there is no dashed rectangle with a resistor inside it next to the symbol for the cell or battery. The high resistance voltmeter measures the voltage across the resistor of resistance R2. We refer to this voltage as the output voltage V out. It's shown in the diagram. The first circuit A consists of two resistors of values R1 and R2. The voltage across the resistor of resistance R2 is half of 6.0 volts. Okay, so here you can see it's moved this way so that the length of resistance wire here is half of this. So that means the resistance here will be half the resistance R2. So the voltage across the resistor of resistance R2 is half of 6. Okay, over here, sorry, 6. This half I already explained it, so now it should be fine. The second potential divider B is more useful. It consists of a single variable resistor. By moving the sliding contact, so this arrow is the wire connected to the sliding contact, we can achieve any value of V out between 0.0 volts. That means if the sliding contact, this arrow is here, that means there is no length of resistance wire across the voltmeter, so then the voltmeter will read 0. But if this arrow is all the way here on this end, that means the entire resistance is there across the voltmeter, which will give the reading 6.0 volts across the voltmeter. So this is what we call the potential divider circuit. This and this, here it's fixed, here you can move this. So two potential divider circuits. It consists of a single variable resistor. By moving the sliding contact, we can achieve any value of V out between 0.0 volts slider at the bottom and 6.0 volt slider at the top. So at the top 6.0, at the bottom 0 volts. By the way, the potential anywhere along this from here to here is 6 volts. Anywhere along this from here, anywhere here, all of this is at 0 volts. At the top here, all of this is at 6 volts. Now here we don't know that. Okay, let's look at this diagram. So anywhere from here to here it is 6 volts. Anywhere from here to here, anywhere there it is 3 volts. Sorry, 0 volts. Then anywhere here, that is 3 volts. So what happens is 6 volts, then because there's a resistance here, it drops to 3 volts. So here the potential is 3 volts, the potential. Okay, so you see 6 minus 3, that is 3. That's how we get the potential difference. That's why we say potential difference. The potential anywhere all the way here, that is 6 volts. The potential anywhere here is 3 volts. The potential difference between this point and this point, which is across resistor R1, is 3 volts. Similarly, here you know, anywhere here the potential is 0 volts. Here anywhere on top it's 3 volts. So again 3 minus 0 will give us 3 volts. So the potential difference across R2 is 3 volts. Okay, so we can write an equation using this. The output voltage V out depends on the relative values of R1 and R2. You can calculate the value of V out using the following potential divider equation. So this is ratio and proportion equation. Okay, that's how we get this. We will see how we can write it and do it as well. Finish this last bit. In this equation, V in is the total voltage across the two resistors. So across these two resistors, it's just one resistor. This is a variable resistor, or you can think of it like this. Across this plus across this, the total is 6, which is V in. You can calculate the value. In this equation, V in is the total voltage across the two resistors. Okay, so now that is the end of that. You can answer this question. Now let's write something about this, and after that we have potentiometers. Alright, so here I have put it in a way that is easy for you all to understand. Look, from here, like I mentioned before, up to here it is 6 volts. So that's why I have written here 6 volts. So the potential here is 6 volts. Now why I am telling this is, there was a question in one of the past exam papers where they had asked this question, and when you go across this resistor, because there is a resistance only, the potential drops from 6 volts to 3 volts, it drops here. So everywhere here along this wire, anywhere, because there is no resistance, everywhere here the potential or voltage is 6 volts. Then over here, because this is a negative terminal, it's at 0 volts. So everywhere here, because there is no resistor in between, from here up to anywhere here, it is at 0 volts. So here it is 3, here it is 0. The potential difference across it will be 3 minus 0. See, 3 minus 0, which is 3 volts. That's how we get this V out 3 volts. V out is the potential difference across R2. This voltmeter is measuring the potential difference across R2, and it will give the reading 3.0 volts. Now if you look at this, here it is 6 volts, here it is 3 volts. So 6 minus 3 is 3. That's how we get the potential difference across this, which is 3 volts. Across R1 the potential difference is 3 volts, across R2 also it is 3 volts, and you can see this plus this should be equal to that, Kirchhoff's second law. Sum of EMFs around a loop should be equal to the sum of potential differences around the same loop. And here it is 3 volts and here also it is 3 volts because the resistances are equal. It doesn't matter if it's 200 or 100 and 100. If R1 and R2 are equal, and if there are only 2 resistors in this loop, the potential difference will be divided equally. Okay, now how do we get this potential divided equation? I will show it to you now. You can see here, V out divided by V in. It's a part to whole fraction, part over whole fraction. This is the part. V out, which is the resistor, the potential difference across R2, that is part. Whole thing is V in, from here to here. The potential difference from here to here is what? 6 minus 0, which is 6 volts. So that is the whole thing. So V out divided by V in. V out part, whole thing is V in, from here to here, that is 6 volts, which is V in, is equal to, so the ratio of the potential difference is equal to the ratio of the resistance. We write another fraction, R2, so it corresponds to V out. See here, because this is V out is across R2, that's why we start with R2 here. R2 divided by the total resistance in that series connection. So from here to here, that is R1 plus R2. So you see, from here to here, R1 plus R2, from here to here also we can say 6 minus 0, which is 6. That's how we get this. Now we can make V out the subject of the equation, and as a result you will get this equation. V out is equal to this. Let me write that. Okay, so you get this equation. Then see, make V out the subject of the equation, then you get this. So it doesn't matter how many resistors are there. Let's say you have 3 resistors in series like this, R1, R2, R3. Then if you want the potential difference across R2, it will be R2 divided by R1 plus R2 plus R3. Yeah, that is the only difference. So V out is equal to R2 divided by R1 plus R2 plus R3 times V in. Again, it's a part to whole fraction. We are having the ratio of the voltages equal to the ratio of the resistance. So this is what we have under the potential divider circuit. This is called the potential divider equation. So here, potential divider equation. I think that ends that part on potential divider. So next part is the potentiometer. Now we will use that concept of potential divider here for this part, and you will understand it. So let's go to the next part, the potentiometer circuits. And there are questions like this, like I said, in the exam papers. It's very simple if you understand how to do this. So let's start that now. Okay, so here is the note now. A potentiometer is a device used for comparing potential differences. So let's say you have to find the potential difference, the EMF. Okay, EMF of an unknown cell, we can use this. So it's used to compare potential differences. For example, it can be used to measure the EMF of a cell, provided you already have a source whose EMF is known accurately. So we know the EMF of, let's say, this cell, which is called the driver cell, and we are going to find the EMF of this cell X, which is we don't know the EMF of. Then say a galvanometer is used to measure small currents, and in this case we are not measuring the current, but we are seeing if there is a current or not. So what will happen is the galvanometer needle will deflect in the direction the current is flowing. For example, if the current is flowing this way to the right, the galvanometer needle arrow will deflect to the right. If current is flowing to the left, the galvanometer arrow or needle will deflect to the left. And if it is vertical like this, that means if it is undeflected, if it's remaining like this where it's not deflected to the right or to the left, if it's remaining like vertical, that means there is no current flow. Now you have learned current always flows from the high potential to the low potential. It flows from where there is a higher potential to where there is a lower potential. We have seen that here. So here you can see it's 6 volts here, and here it is 0 volts. So that's why the current flows from here to here. So it flows from 6 volts to 3 volts because here the potential is higher. It's 6 volts here. Here the potential is 3 volts. So current always flows from high potential to low potential. Now in this case, what we are doing is we have a wire here, conducting wire. Okay, potentiometer wire. So what will happen now? The current will flow like this, it will go like this. Now if the potential here is less, then what will happen? The current will flow through this also, because the current always flows from high potential to low potential. So we have seen that this can be used to charge a battery. For example, if you have batteries with opposite terminals facing each other, and if one battery has the same terminals facing, that battery can be charged in that way. But so this is something similar. Now if the potential, you see over here, is greater than the potential difference across these 2 points AY, then what will happen is the current will flow, and some current can even flow this way, and if it is a rechargeable cell, it can recharge this. Now what we are doing here, why we have the sensitive galvanometer, is we move this arrow, we move this, you can think of it like a sliding contact. Actually there are paper 3 practicals on this. So what we do is we use a wire with a crocodile clip, and this wire AB is attached to a ruler. So you have a long meter rule, and the high resistance conducting wire is attached to that meter rule. So that way you can see what is the length of the wire. So maybe from A to B it is 100 centimeters, then from A to Y maybe 30 centimeters. Like that you can move this sliding contact. So there's a wire connecting to a nichrome tungsten constantan wire here AB, and you can move the sliding contact. You can find the point where the ammeter gives a 0 reading. Now in this case the galvanometer. Now when you move this, what will happen is if you move it to this side or to this side, this will deflect. So you can find where is the point Y on this red wire AB that will cause this to not be deflected to the left or the right. Now when it is not deflected, that means the potential here and the potential here are the same. So for example, let's say the potential difference here is we'll say 3 volts between this point and this point. Okay, and let's say the potential between AY, this point and this point, is also 3 volts. Then what will happen? The current won't flow through this because they are at the same potential. Now for current to flow, they should be at different potential. So basically what we are doing is we are moving this. So here let's say from A to Y the resistance is AY. From here to here the resistance is AY. From here to here the resistance is YB. Okay, and when you move this sliding contact to this side, what will happen? AY decreases, resistance AY decreases, because R equals rho L over A. So when rho is the same, because it's the same via AB, A is also the same. So what happens is when you decrease L, the resistance AY, okay, so if this is AY, that decreases, and that's what that's why we are using the length here, because rho and A are constant. Now if we make LAY, which is what we have here, the subject of the equation, rho and A, they cancel out. So instead of R we can write the length. That's what That's how we got this equation. I can show you the derivation, but basically you can remember the length is proportional to the resistance, so that's how we can use this in this equation. Now what happens is, if this arrow here is moved to the right, what will happen is the resistance here will increase. If you move this here to this side, you have a longer length, so the resistance here will increase. That means the potential difference across AY will increase. Between this point and this point it will increase. Now here the potential is the same, because this is a cell with the fixed EMF. This potential doesn't change here, the EMF here doesn't change. So let's say we move this to this side, and so let's say, let's go back. Okay, so from here, okay, so let's say this arrow is moved to the right. Then what happens? The length increases. That means the resistance AY is higher now. So let's say when V equals IR, okay, so when this increases, the V increases, the potential difference across it increases. Now what happens? The potential here between these 2 points increases. So let's say this is 3 volts. Now let's say we move this to this side, it increased to 6 volts. Now what happens? Here it is 6 volts, and let's say this is like 9 volt. Okay, so what will happen is there will be a current flowing through this as a result. Okay, so then this needle will deflect. Now we don't need to go into so much detail. What you can easily remember is this equation, then you can apply it directly. Okay, so we will find the point where this needle is not deflected, and that is where the potential here. Now let's say we know this is 3 volts, so from here to here there will be a point where this needle is not deflected. Okay, so what you can do is you can find that length. Okay, so let's say the potential across these 2 points will be the same as the potential difference across this. You can find it using this equation. Then now you know E naught, that one you know, and you know this length, and also you know the length here, you can measure it, and then you will see you can find this. It's very simple. So because the potential between these 2 points and the potential between these 2 points are equal, the current will not flow through this path, because for current to flow there should be at different potentials. So what we are basically doing is finding the potential difference across these 2 points, which will be equal to the EMF of this cell. Okay, and to do that we can use this equation and get the answer. So what you need to understand here is, again, like the potential divider circuit which we saw earlier, we are using ratio and proportion. The ratio of the resistances is equal to the ratio of the potential differences, and in this case, instead of using the resistances, because R equals rho L over A, rho the resistivity, it's the same wire, and A are constant, we can say that we can use L instead of R. So that's how we get this. Now look, this is part, right? This is the whole thing. So EX divided by E naught equals the part length is AY divided by the whole length is AB. That's how we get this equation. So this is what we will be using to find the EMF of an unknown cell. Okay, so here I have shown the working, but like I said, this detail here you can just learn it. You don't need to learn the derivation, because otherwise you might wonder how I got this. So this is how we do it, very easy. We use the Kirchhoff's second law for this loop here, which states that the sum of EMFs around the loop is equal to the sum of potential differences. Now when this happens, we know the potential difference across this and across this AY, across this and this are the same. That's why the galvanometer needle won't deflect. So they are the same potential, which means no current flow here. So we are considering that and doing this now. Now if you go around this loop, the EMF is equal to the potential difference across this VAY plus the potential difference across this VYB. potential difference across this plus the potential difference across this. And you have also learned R equals rho L over A. Now if you look at this length of wire, it's the same wire, so rho and A are the same. Rho and A is the area of cross section, rho is the resistivity. It will be the same because it's the same length of wire. A is the area of cross section. And you have also learned V equals IR. Now for R I can write this, so that's how I got this, you see here. Now this I substitute for VAY and for VYB. Now it's the same current which is flowing through this path here and here, because no current flows through this path. When they are the same potential, the current, no current flows this way, so whatever current that is going this way, it will go through this path and go that way. Now even though this point and this point are at the same potential, here and here they are on the same potential, so that's why the current flows through this path and does not flow through this path. So the potential between these 2 points and the potential between these 2 points are the same. That's why EX, the potential, the EMF EX is equal to the potential difference across AY. So we will see that. See here I wrote the potential difference across AY is equal to the EMF of the unknown cell EX. X letter normally we use for something unknown. Alright, now you have this is very clear, I guess, from here. I times rho. Now L is the length AY, that's why I write AY here, divided by, similarly for this length YB. Now I, rho, A, they are the same for this term and this term, so I factor it out. See, I factor it out. Okay, and now what do I have? This, I have this. Now here you can see LAY plus LYB, the length AY plus the length YB is what? The length AB. That's why I wrote it here, length AB. Okay, now for EX also I can write the EMF EX is having a magnitude equal to the potential difference across AY. So VAY, and the potential difference across AY you can see is this I times R, and R is rho L over A, so then I can rewrite that here. Now the final step is, so we can call this equation 1, this one equation 2. So what we do now is EX divided by E naught. First equation divided by second one. EX divided by E naught is this whole thing divided by this whole thing. So when you divide, I, rho and A are the same for both the numerator and the denominator, so I can cancel it out. I haven't shown that, but you can do it on a paper and you will see this will be in the numerator, this will be in the denominator. It's the same value, I, rho, A. Here also I, rho, A, so we cancel that out. Then what are we left with? This and this, so it's length AY divided by length AB, and that is what we have here. So when you rearrange that, you will get this equation. So this is the equation that we are using to find the unknown EMF. So you can go ahead with this directly, but I showed you the derivation, and it is also, I think, explained here. You can see this column explains that about zero deflection, and this is the jockey. You can move this along the length of high resistance wire. These wires are usually nichrome, tungsten, constantan or manganese, but tungsten we don't use in the lab. We are using normally nichrome, constantan. Yeah, those are the values, those are the materials we use. Okay, so details are listed here. When you do the paper 3 practical also, you will understand this better. The potentiometer can be thought of as a potential divider, because the point of contact Y, see, you can move this point of contact Y, divides the resistance wire into 2 parts. Okay. 2 parts, AY and YB, equivalent to the 2 resistors of a potential divider. It's similar to what we have here. See, here we have the sliding contact. This is also like a sliding contact. We use a crocodile clip and move it along the resistance wire which is attached to the ruler, so that way we can measure the length and we can do this kind of experiment. Like I said, in paper 3 there is a question where you need to do something like this. Okay, so that's the end of the potentiometer circuit. Now you know how to get this equation, ratio and proportion, part over whole fractions, and how we get it also. Why the IA rho cancels out also I said, because it's the same current. Remember, when we are using this equation, we do it at the point where V is, so that this doesn't deflect, or the current here is 0. That will be when we can use this equation. So no current is flowing this way, all the current is flowing through the wire AY and YB, which is via AB. So all the current through AY is the same as the current through YB, because this is at the same potential as this. So the EMF here, EX, is equal to the potential difference between AY, which is VAY. Okay, next we will see how we can compare EMFs with a potentiometer. Again, that is also very simple. You can again use ratio and proportion like what I explained previously. So here you can see, so very simple, EX, the potential difference or the EMF of this, EX divided by EY. So see, part over whole, EX divided by EY. Now how do we know this is part over whole? Because this is a smaller length and it's the same length of wire. ACDB is just a single wire. ACDB, or we can say simply AB, is a single wire. So rho and area of cross section A are the same. That means now we can directly use this equation. That means EX divided by EY, see, EX divided by EY equals AC, the length AC. Okay, here they just use the letters AY and AC, but it's actually the length AC divided by the length AD. So again, part over whole fraction, EX divided by EY is equal to AC divided by AD. So let me just read this bit. Comparing two EMFs using a potentiometer, the ratio of the EMFs of the two cells will be equal to the ratio of the two lengths AC and AD. See, the ratio and proportion. If one of the cells used has an accurately known EMF, so if you know the EMF of either of the cells, the other can be calculated with the same degree of accuracy using this equation. Comparing EMFs with a potentiometer. I'll just read this paragraph quickly. When a potentiometer is balanced, no current flows from the cell being investigated. This means that its terminal. So here also, by the way, this should not be deflecting. Again, no current is flowing through this path, no current is flowing through this path. Then only you can get this equation like I showed you over here. You can get this equation. This equation is true only when there is no current flowing through this path and it is connected like this, so that the potential difference across AY is the same as the in magnitude to the EMF of the cell here. Same thing applies here as well. So we have moved this point C, point D, the wires C and D, so that there is no deflection in here and here. No current flows through the cells being investigated. This means that its terminal potential difference, so terminal potential difference, we assume there is no is equal to its EMF. So terminal potential difference equal to the EMF. No current flow. Remember, that was the first thing we learned here. Okay, so terminal, when I is approximately equal to 0, the EMF is equal to the terminal potential difference. I showed it to you in the very beginning here. With the voltmeter, we can use that method to find the EMF of the cell. We do not have to worry about any lost volts. This is a great advantage that a potentiometer has over a voltmeter. See, potentiometer has over a voltmeter, which must draw a small current in order to work. Now, I told you voltmeter, for it to work, there is a current flow here, but it's a very small amount. That's why I wrote this as I approximately equal to 0. But in this case, no need of that. No need of any current flowing when we are using the potentiometer to measure to find the EMF or compare EMF. However, there is a small problem. The driver cell is supplying current to the potentiometer. See, current is flowing this way through this first loop only. And so the potential difference between A and B will be less than the EMF of the driver cell. Some volts are lost because of the internal resistance of this. Now, they haven't shown that in the diagram, but anyway, all the cells have an internal resistance. To overcome this problem, we use the potentiometer to compare potential differences. Suppose we have two cells. Okay, so this method can be used to overcome that, but here there is an internal resistance here. That's why it's a better method to use this one. Suppose we have two cells whose EMFs EX and EY we want to compare. Each is connected in turn to the potentiometer, giving balanced points C and D. See figure 19.2. By the way, they are connected in turn. In the diagram, you can see immediately that EY must be greater than EX because D is further to the right than C. The length here is longer. AD is longer than AC. So see, suppose we have two cells whose EMFs EX and EY we want to compare. Each is connected in turn to the potentiometer. Okay, then we can do it from here. In the exam, basically you are directly using these equations and doing it. You don't need to go into details about the derivation like this. Okay, so I think that is the end, and we'll write a quick note about this last part, which is the comparing EMFs with the potentiometer. Alright, so here we have it. The current through this path and this path is 0, and this is basically everything summarized about comparing EMFs with the potentiometer. And remember, we connect each one in turn, this in turn, and then this one to the potentiometer. And remember what a potentiometer is. It is a device used for comparing potential differences. Okay, for example, it can be used to measure the EMF of a cell. That is what we saw here, provided you already have a source whose EMF is known accurately. Yeah. So potentiometer can be thought of as a type of potential divider circuit. And finally, we saw how it can be used to compare the EMFs, and the advantage of this compared to the one here. Here, the disadvantage is there is a current that is flowing through this, so internal resistance is there here, so the terminal potential difference will be less than the E naught here, but we are using this E naught here. But over here we can overcome that problem. Okay, so to overcome this problem, we use the potentiometer to compare PDs. Suppose we have two cells, EX and EY, we want to compare. Each is connected in turn to the potentiometer, giving balance points C and D. See figure 12.9. In the diagram, you can see immediately that EY must be greater. Okay, so we went through this already, and that is the end of this lesson. Okay, the same way you can even compare the potential differences. Okay, so there are questions like this also. Okay, comparing potential differences, the same technique can be used to compare the potential differences. For example, two resistors could be connected in series with a cell. See, two resistors connected in series with a cell, this one. Okay, so one separate circuit here, another one here. The PD across one resistor is first connected to the potentiometer. So here you connect this with a wire and then connect here, and we can see when we move it somewhere along this length, the current will stop flowing through this. The galvanometer needle doesn't deflect. The potential difference across the resistor is first the potential difference across one of the resistor is first connected to the potentiometer, and the balance length is found. So you can find at what length that there will be no current flow in this path. So here there is a wire, here we have, then there will be no current flow when the potential difference between these 2 points and these 2 points are equal. Between these two and these two are equal potential differences, no current flows. This is repeated with the other resistor, and the new balance point is found. Same thing we do here. The ratio of the lengths is the ratio of the potential differences. So it's very simple. The length from here to here divided by the length from here to here will be the length from here to here. You can see that way you can get it. Since both resistors have the same current flowing through them, the ratio of the potential differences is also the ratio of their resistances. So we can say V1 from here to here, let's say V1, okay, divide by from here to here, let's say V2 is equal to R1 divided by R1 plus R2. Or else we can say from here to here V1, let's say from here to here V2, okay, then V1 divided by V2 from here to here is equal to R1 divided by R2. So that's what is there, comparing two potential differences using a potentiometer. Now quickly let's go through the summary. A source of EMF, this is very important, make sure you understand everything here. Source of EMF such as a battery has an internal resistance. We can think of the source as having an internal resistance R in series with an EMF E. So we saw the diagram for that like this. The terminal potential difference of a source is less than the EMF because of the lost volts. You can see here, this is the lost volts. The equation in words is here. A lost volt across the internal resistance. A potential divider circuit consists of 2 or more resistors connected in series to a power supply. You saw it here. So it can be 2 or more. Then this will become R1, R2. If there are 3, it will be R plus R3 also. The output voltage V out across the resistor of resistance R2 is given by this. A potentiometer can be used to compare potential differences. Okay, so that's the end of that part. So make sure you answer all these questions and check the solutions, because that will ensure that you understood the theory very well. Now in the past papers also there are some questions like this, so make sure you understand this. Maybe we can write something quickly about this also and end the lesson here. Okay, so this is what it means. If you just look at this here, the ratio of the lengths is the ratio of the potential differences. So the length AB divided by the length BC is equal to potential difference across this divided by potential difference across this. So that's what I have shown here, VAB divided by VBC. Since both resistors have the same current flowing through them, the ratio of the potential differences is also equal to the ratio of the resistances. Okay, we'll write that all. Okay, so this is what we have. Okay, so R1 divided by, see again, ratio and proportion, part over whole fraction, R1 divided by R2, AB divided by BC, see AB divided by BC, AB divided by BC. It can be the length, it can be the potential difference, or it can be the resistance, R1 divided by R2. So but remember, you have to write it in the correct order. If we start with this divided by this equal to that divided by that. This is the length that is corresponding to R1, AB. BC is the length corresponding to R2, like that. Same thing you can do from here to here also, but I think it's clear now. Okay, so that's the end of the lesson on practical circuits. We went through internal resistance, potential dividers, and the potentiometer circuit. So make sure you answer all these questions in the brown boxes first and check the solutions to ensure that you have understood the theory very well. Then you can start the end of chapter questions. Do this also and check the solutions in the CD-ROM part of the book, in the last few pages of the book. It's also coming in the CD separately. Alright, let's end it here. The next lesson is the next chapter.